Hey everyone, so today we're just going to do a kind of straightforward lesson on just how we are able to turn word equations into those chemical formulas that we're going to be working with for the next couple of weeks. So this isn't anything very different from what we did before, where we're talking about the nomenclature and we're just kind of like translating it from a word into some kind of chemical formula. So anytime you have any kind of a chemical equation that you've got to work with, you want to make sure that you put it into a chemical formula, because that makes it a lot important to do things like check to make sure you have the right numbers in front of everything so that we have a balanced equation. So we'll talk more about balanced equations later, but just keep in mind that we need to translate anything written, into some kind of chemical formula. So the first thing that we want to understand is that we actually have generally just two parts to a chemical formula. So we have our reactants, and those are the things that are going to be reacting with each other and going to form something different. So these are our starting products. This is kind of like our before. And we have this little arrow, and that arrow is showing that these things are going to now become something else. So this arrow is demonstrating the actual reaction that occurs, and the reaction that occurs creates some kind of product. So hopefully those words make sense. The reactants are different chemicals that are going to react with each other. So they're going to be able to break down bonds that are holding each other together. We talked about those a lot with like ionic bonds. Those will happen much more than covalent bonds to break down. And then once those bonds are broken, then they can go and connect with a different type of element to form a new bond. So here, again, reactants. And then on the other side, the thing that we create is a product. So if we take a look at our word equation, we want to pick out where those reactants are. And right off the bat, I can see that I've got a reactant in zinc, and it's telling me that this reacts with hydrochloric acid. So I know those are going to be my reactants. I also want to pay attention to what the states are. So in this case, the zinc is a solid zinc. And this is going to be important a lot more in the future if you're continuing on with chemistry. But I always think about including the states as almost just like good hygiene. In the same way that you want to brush your teeth and floss, you want to make sure that you're doing these little steps just so that you're building your chemistry know-how and your chemistry practice. So we started off with our reactants. So we've got zinc. So I'm just going to write the symbol for zinc down here. And it says solid. So I'm going to put this little S beside it to indicate that it is solid zinc. So when we are looking at the next one, here we've got hydrochloric acid. And if you recall from when we were doing our naming or nomenclature, when we have the long name here, we've got that hydro in front. That's the sign that it's going to be a shorter formula. So hydrochloric acid is a shorter formula, which means that it only has two elements, one of them being hydrogen. And since it says chloric here, I know that it's going to be chlorine, because that's the one that sounds closest to it. And so I'm going to put that HCl down to represent hydrochloric acid. And we know that we need that little AQ sign there, so that we are showing that this is an acid. So acids all have to dissolve in water. And we talk about AQ, aka aqueous. And that just means that when this happens to get into water, it separates from each other. So you don't have to worry about this too much, but for those of you who want to know, hydrogen actually separates into its own ion, and then chlorine separates into its own ion. So that's what that term aqueous means. Okay? So here I've got my reactants put down, and these are going to create or produce aqueous zinc chloride and hydrogen gas. So I'm going to put my arrow down here to show that the reaction's happening, and then on my other side, on my product side here, I'm going to put that zinc chloride. And anytime I'm writing a formula, I always want to go back to the charges. So if I'm looking at zinc here, I can see that zinc is number 30. And since it's one of these transition metals in the middle, or lead and tin over here, I'm going to double check whether or not it has more than one charge on it. And then zinc, wonderfully, only has like a charge of +2. So I don't have to worry about any of those multivalents. If you do happen to come up with one that, like if you're starting off with an element, a metal just by itself, and metals can just be by themselves, then you want to make sure that you are checking the back just to see if there's any charges. And if it's not given to you, then you can kind of just pick one of the charges, but make sure it's something that applies. So since zinc is going to have a charge of +2, I do that cross down. So that +2 would have been up here, that -1 would have been here. I cross down so that I have zinc Cl2. And we're also going to have hydrogen gas. Oh, sorry, I almost forgot to put aqueous there, AQ. We're also going to have hydrogen gas produced. And so hydrogen is one of those types of elements that are always found with a partner. So if we're ever talking about hydrogen, there's never a single H, it's always H2. And so one way that you can remember this, because there are a few things that are called diatomic elements. Give me 1 second, the lights just turned off. Okay, so they're called diatomic elements, and these are ones that are always found in pairs. And there's a couple of different ways you can remember it. One of them is almost kind of talking about, almost like somebody's name, like Hoffenbrinkel. And if we look at these, you can also use the shape of the periodic table to help you remember. So part of that Hoffenbrinkel is we're talking about hydrogen over on this side, but all the other ones are actually connected together here. So we have nitrogen, oxygen, fluorine, chlorine, bromine, iodine. So it makes this almost like a little 7 here. So the ones that are along the top and the ones that go down that last column before our noble gases, and then hydrogen. So you can almost think about it as a 7 and pointing to our solo friend over here, hydrogen, or you can think about it as Hoffenbrinkel, whichever one helps. But what it means is that all of these are going to be found in pairs. So if we're ever talking about hydrogen, we're talking about H2, oxygen, O2, fluorine, F2, iodine, and you kind of see the pattern here. So all of these are going to have a 2 on the bottom anytime you see them where they're just written down by themselves. Okay, so diatomic, and of course, di happens to mean 2, and atomic is talking about the number of atoms that we have. So this is one example where we'd have our solid zinc, we've got our aqueous HCl, we've got aqueous zinc chloride here, and then we put a little G there to stand for our gas that's forming. Because when hydrogen reacts, we often get that gas form, because hydrogen is often found as a gas. You can also just tell the states, looking at the periodic table, they've got this nice little legend over here that tells you what the colors mean. So let's just do one last example. If we're talking about something like magnesium hydroxide. So again, we're looking at what are our reactants. And the reactants go on the left side of the equation. Just like we read from left to right, we write down these things from left to right as well. So here we've got magnesium hydroxide. So I find that magnesium on the periodic table. Because it says hydroxide, I don't actually see an element on the periodic table that says hydroxide. Also, the name itself, it almost looks like hydrogen and oxygen squished together. So I'm going to take a look on the back of my periodic table at the polyatomics, and here I can actually see hydroxide right there. So I know that this is going to be OH. It's a good idea to just put brackets around your polyatomics just to remind yourself that these things belong together. And then we're going to do that cross down. So magnesium, we have that 2 there. Hydroxide, we have that 1. And we're going to bring the 1 down here and the 2 down here. So I'm just going to do that here and cross out the charges. And of course, I don't write that 1 there because we just generally don't show when there's just 1 of something. It says that it's going to be aqueous, so I'm going to put that AQ here. And it says that this is going to be reacting with phosphoric acid. So if you remember what we were just talking about, Here we actually have a shorter name. We don't have that hydro there. So a shorter name means a bigger compound. I start off with my hydrogen because that's what all acids are going to start off with. And I'm going to take a look at my polyatomics because anything that doesn't have hydro in front of it, that's an acid, has more than just 2 elements. And I can see that the one that's closest here is phosphate. So that's PO4 with a charge of -3. So I'm going to put that PO4 here. That charge of -3 is going to go down here. So I'm going to drop that down, cross it out. Hydrogen just has a 1, so I don't have to put anything there. But of course I have to put that AQ because the AQ is what tells me that it's going to be an acid. So all acids have that hydrogen and that AQ, aqueous sign. I'm going to do my arrow here. And then if you happen to see water, unless it says that it's like water vapor or water gas, it's going to be a liquid. When we talk about aqueous, we talk about things almost like dissolving really well in water. And you can't really dissolve water in water quite so well. So since whenever you see that water represented, if it doesn't say otherwise, it is a liquid. And so here, this is like my little cursive L, just so it doesn't look like a 1. And this is talking about a liquid. And then magnesium phosphate. So here's my Mg, that should be a PO4. Magnesium has a charge of 2. Phosphate has a charge of 3. So I'm going to bring that 3 down here and put those brackets around my phosphate so that I'm keeping this together and I'm not changing. If I'm changing everything, I'm changing this whole unit. I'm going to bring my 2 down to the other side. And sorry for squeezing this in here. And this says solid, so I'm going to put that S there. Okay? So here we've got aqueous magnesium hydroxide plus phosphoric acid, always that AQ and the hydrogen for the acid, gives us liquid water, and then here we have a little S for that magnesium phosphate. Hopefully that made sense. You're just going to get a lot of practice with that because we're going to be